Avogadro's hypothesis, which states that the equal volume of all gases contains equal number of molecules under similar conditions of temperature and pressure. As we have also discussed about the reaction in the case of a hydrogen with chlorine forming HCl. Okay, I can also consider hydrogen with the oxygen forming water. Okay, so I can say that here it is 2 volume of oxygen and here it is 1 volume of oxygen which undergoes reaction to form 2 volume of water. Or if I consider that if n number of molecules is present in V volume of the solution or the gas, then I can say that it is 2 molecules of hydrogen which undergoes reaction with 1 molecule of oxygen to form 2 molecules of water. Or it is 1 molecule with half molecule of oxygen forming 1 molecule of water. So I say that 1 molecule of water is equal to, like, it has half molecule of oxygen. Okay, from which I can say we can calculate, I can give a calculation for the atomicity. So let us explain the applications of Avogadro's hypothesis now. So dealing with the applications, so it helps in the calculation, it helps in finding out the atomicity of an elementary gas. So that is the first application. Atomicity of an elementary gas can be worked out with the help of this law. How? As how we have discussed here, like one molecule of hydrogen will undergo reaction with half molecule. So when I say half molecule of oxygen, it means it is 1 atom of oxygen. So when I say 1 molecule of oxygen, it means it has 2 atoms of oxygen. So in that way, I can say that atomicity of oxygen is 2. So hence it is used in the application, as an application in calculating the atomicity of an elementary gases. The second application is to derive the relation between the mass and the vapor density. Vapor density, it's actually what we say density means generally you know that is mass by volume. When we say vapor density, what we use is we compare it with the standard value, reference gas. So what we use is the relative density, which we call it as a vapor density for the gases. So this vapor density, so I consider the standard or the reference gas, here it is hydrogen. Okay, for the gases we consider hydrogen as a standard element, okay, standard molecule. So in this case, vapor density will be density of a gas to the density of hydrogen. That will be the relative density, which we call it as a vapor density. So as we know very well that density is mass by volume. Okay, so I consider this as mass of certain volume of a gas at STP by mass of certain volume of hydrogen. So if I consider n molecules are present in a given volume of gas and hydrogen under similar conditions of temperature and pressure, then I say that vapor density will be equal to, okay, let me consider small n because capital N has different value. So let me consider small n. Okay, in that case I'll write it is mass of n molecules of gas to mass of n molecules of hydrogen. So which is again mass of 1 molecule of gas by mass of 1 molecule of hydrogen. Mass of 1 molecule of hydrogen is 2 into mass of an atom, 1 atom of hydrogen. So this ratio that is equal to the molecular mass. Okay, this ratio is equal to that of the molecular mass. So we write it as molecular mass divided by 2 is equal to vapor density. So we say that molecular mass is equal to 2 into vapor density. That's the relation with the molecular mass and the vapor density. That's the second application. Going ahead with the third application. So what we have discussed is the relationship between the molecular mass and the vapor density. Molecular mass. Let me highlight its molecular mass. Okay. So it's the molecular mass and the vapor density. Now the third application what we are going to discuss is the relationship between the mass and the volume. Mass and the volume of a gas at STP. So we have already discussed that molecular mass is equal to 2 into vapor density, and we have told that vapor density is mass of certain volume of a gas at STP by mass of certain volume of hydrogen. So I can consider the certain volume to be 1 liter. So I can write this as 2 into mass of 1 liter of a gas at STP by mass of 1 liter of hydrogen. Okay. So that will be equal to 2 into mass of 1 liter of gas at STP by mass of 1 liter of hydrogen is found to be 0.089 gram. So what we have is 2 by 0.0889, which is 22.4 liters. 22.4 the value is. So into mass of 1 liter of a gas at STP. So this will be equal to mass of 22.4 liters of a gas at STP. So this is how we relate the mass and the volume. Okay. So let me work out for this. Okay, we know that it is the density of hydrogen is 0.00089 gram per ml, and volume 1 liter is equal to 1000 ml. So we have density is equal to mass by volume. Density is known, volume is known. I have to